Very exciting to be in Los Angeles, although it still feels like Oregon. So I have this weather for consecutive 4 months in the winter, so I was expecting to see something different. Anyway, so I'm going to talk about representation learning today. So it is a terminology that has been talked about for quite a while. You could have a lot of perspective for looking at this terminology. So today I'm going to share my take from a signal processing viewpoint, as Tulay said, blind source separation viewpoint. Okay, so representation of data matters in machine learning, right? So when we talk about the data in machine learning, we cannot just use the raw data. We need to first represent the data using a vector, a matrix, or a tensor in a certain space, and then we use the representation fit to a learning system and do our tasks, right? So in the old days, this was called feature engineering, and in the old days, we used a lot of handcrafted features like vertical occurrence, term frequency, right, and bag of words. All these things were we call this handcrafted because they were constructed following some pre-specified rules by ourselves. Now, more recently, we're using a lot of data-driven learned features. For example, if you use dictionary learning, or more prominently, neural networks, right? So this is a figure that very nicely illustrates the idea of using neural networks as feature representation learners. This is your raw data. You feed it to a convolutional neural network, and it propagates through a lot of layers, and then you have a vector representation of your data, and at the last layer, you can treat it as a linear classifier. Neural networks as representation learners have achieved a lot, right? So in just 1 decade, it has brought down the error rate of some very complicated tasks like classification of ImageNet with just 1,000 classes, from very high error rate to an error rate that is below human perception error rate, right? Fascinating. More importantly, we have seen industry booming, right? A lot of new companies, startups, successful companies developing based on the frontier research of artificial intelligence. This is really transforming our society. At some point, right, they have so many success stories. So at some point, you really feel that is our society going to be taken over by the AI? Right? When I was looking at these pictures, do you know this story? So this is the then #1 Go player in the world, beaten by AlphaGo. When I was looking at these figures, I was like, my Terminator nightmares are coming true. But anyway, right, so is deep learning already at a level of perfection already? When you look at the machine learning, deep learning models long enough, you realize that, okay, of course not, right? The deep learning models also have the problems that we solve for any other machine learning models. Let me give you an example, right? This is a nice example that I found from this paper. So this is object recognition task. You train a deep neural network, and you wanted the neural network to recognize that there is a cow in these figures. Now, when you feed this, the leftmost image to your neural network, train the neural network, of course, it tells you that there is a cow here. But when you feed these 2 images to the network does not realize that there is a cow, which makes sense. Why? Because when you train the neural network, the cow appears with this environment very often, right? This is a typical environment where the cow appears. You have grass, you have a mountain, right? You have a pasture, like a farm, but the cow rarely appears with a bitch, right? So that's very typical, right? And this is what we call overfitting, right? And neural networks easily overfit, right? You have a huge model, you have limited labels, and this is the source for overfitting. Your neural network, when you train it, right, overfits to the environment. You want to extract a representation of the cow, but the neural network also uses the environment information to represent the cow. And because it's a black box, you don't really have a lot of control on how the neural networks extract the features to represent your object, right? And this leads to the fact that for effective deep learning models, you normally need a huge amount of data to train a good model. For example, here is a nice illustration. If you want to train a ResNet 50 to do the ImageNet task, as we mentioned before, this means that you have roughly speaking, a 50-layer convolutional neural network. Then if you use 100% of all your data, right, which means 1 million labeled data with over 1,000 classes, the performance is good, very good actually. The top 5 accuracy is almost 95%. But if you reduce your training sample to 10% of all the training data, which means 100K, the performance drops drastically, right? If you only use 1%, this is terrible. But using 10% is already a lot, right? The annotation workload is not trivial, right? So this means that this is quite costly, and we all know that, right? This is like a commonly known knowledge that deep neural networks are very data hungry. So our question here is, can we learn good representations of data using limited or even no labels, right? To answer this question, we need to first have some ideas about what is a good representation, right? So there are a lot of discussions in the literature from the last decade about what makes a representation good, right? I found from the literature that 2 points are particularly relevant. Now, first, the representation of your object should be invariant across different things, right? What does it mean? It means that if I want to represent the cow, I wanted the representation of the cow over these different things are identical or similar, right? Which makes sense. Second, if I want to represent the cow, I want to use the essential information from my data, but not redundant information. I just want to use the pixels that are related to the cow, but not the pixels that are related to the environment, right? Okay, so these are the 2 points that are particularly useful to help us to find essential information. Now, how do we do that? If we want to achieve this goal, if we want to make our representation satisfying these specifications, there's one way that is the classical way in machine learning and statistics can help you to do this. It's called multiview analysis. Well, what is this? Multiview analysis aims to extract common information across multiple views or multiple modality of your data or event, right? Let me give you an example. Now, these 2 pictures can be considered as 2 views of a cow, right? Now, if you ask your representation learner to extract common information from the 2 views, naturally, the learner will be more focusing on the identity of the cow, right? But largely discard the grass and the water, the mountain information. Why? Because they were not in common, right? What is mostly in common is that there is a cow, right? So this can help us extract, right, the cow information, which is the same environment, and also discarding redundant information. Very naturally. It's not a new thing, right? It's a very classic thing in machine learning, in signal processing. And multi-view data is actually often not very hard to acquire. When something happens, an event happens, you can record the audio and the video or the image of the event, then you naturally have multiple views, right? And if you look at text data, nowadays a lot of text data have translations. They can also be considered as multiple views of your data. And if you don't have multi-views, you just have a nice figure of your dog, you can still create multiple views by yourself by just cropping, right? Cropping, adding noise, and rotating, right? Just creating different views of looking at the dog. So this is actually people call data augmentation these days in self-supervised learning, which I will come back to. And it really works. Right, let me give you a toy example. I have two views of handwritten digits. This is a clean view. This is a rotated and noisy view. If I just use single view to learn a low-dimensional representation, 10-dimensional representation, and then I project them onto 2 dimensions to visualize. If I just to use one view, the visualization of the digits are still coupled with each other, right? If I use the 2 views simultaneously, you can see that they give us quite a nice and cleaning clustered structure, which is very nice, right? And no label was used. Okay, so it was nice, but how do we do it mathematically? Again, there's a very classical tool that can help us. This is called canonical correlation analysis. The origin of this method could be traced back to 1930s, before World War II, right? So what is a CCA? If you write down CCA using an optimization formulation, it looks like this. Now you have X1, which is the data from view 1, X2, the data from view 2, they correspond to the same thing, the cow or a car or a dog, right? And then you want to find, remember, we want to extract the common information. So you use 2 linear operators, B1 and B2, applied to your data, such that the transformed data B1x1 and the B2x2 are as close as possible to each other in Euclidean distance sense, right? So because you wanted them to be common, so you wanted them to be as close as possible. Of course, you do this normalization to and the whitening to make sure that the learned representation to have little redundancy in terms of linear dependence, right? That's the mathematical formulation. And then you have a lot of data, so you take an expectation. This is called correlation analysis because the objective function is equivalent to maximizing the cross-correlation of the learned representations from the 2 views, right? And of course, in practice, you only have finite samples, so you add an index here to represent the samples and do sample averaging. That was almost a century ago, and we have been using CCA like forever, right? But we all know that if you just use a linear transformation to transform your data, you have a very limited transforming power, right? Because the linear operators, what does they do? They do rotation, scaling, rotation again, right, by SVD. So naturally, people are thinking, okay, let's change the linear operators to nonlinear operators, right? You can use kernels, but perhaps these days people use deep neural networks more. So if you change the B1, B2 to nonlinear mapping represented by deep neural networks, this gives you the deep CCA formulation, right? If you visualize deep CCA, it looks like this. And it really works better than linear transformation. The same example, what I showed you was basically done by deep CCA. And if you use a linear CCA, it's promising, but not really having this nice structure, right? Okay, this is, but the deep CCA appeared in 2013. That was a decade ago, right? More recently, people were talking about self-supervised learning. This actually, if you look into the objective functions of these paradigms, you will realize that they share a lot of similar concepts as we saw in deep CCA, right? So now you have 2 views in self-supervised learning, X1, X2. Now the X2 is augmented by yourself, right? So this is created by cropping and rotation, so on and so forth. And then, right, if you look at the objective functions of these popular frameworks, it's still, you find 2 different neural networks trying to matching the latent representations extracted by these 2 mappings to make them as close as possible. Right? This is exactly what we saw in DCCA. Of course, there are a lot of details that are different, but the high-level ideas are quite similar. Now, the more recent one called Barlow Twins, this is from meta-research from the last year, is doing this objective function, which is seemingly different from here, but if you look closer, what is this doing? This is trying to make the cross-correlation of the extracted representations from the two views to be close to identity, as close as possible, right? So this, if you visualize this, is still very similar to DCCA. Again, matching the representations extracted from two views. And self-supervised learning, right, is really, really attracting a lot of attention. And why is that? The major reason, perhaps, is it really works beautifully. As I mentioned to you, right, if you just use supervised learning and 10% of the training sample of ImageNet, you get not so good performance. But think about this. You can use all the training data, 1 million training data, without knowing their labels. You just feed them to this self-supervised learning objective, and then you learn representations as pre-training, right? And then you use those pre-trained representations to work on 10% or 1% of the labels to train a simple classifier. And then you observe what is the result. Immediately, you get a almost 10% accuracy bump here, right? Now, if you look at this, you get almost the 30% of accuracy increase, which is amazing, right? Because this stage does not really use labels. And then you just use 1% or 10% of the, yes? What? Excuse me. As for it, yes. I don't really understand why is that, but that's also something I noticed. Yes. Yeah, because, or this perhaps would introduce some other level of error, because this becomes a two-stage approach, right? So I don't really understand this part, as you also noticed, but this part is perhaps the reason why this is really attracting a lot of attention.
And a quick question: can you select 1% by percent for your regular error?
I think this is done by random. Okay. All right. Okay, so, but our question as signal processing people is always why this happens, right? So we want to understand this at least from a more top-down angle. Because self-supervised learning has been so useful in image classification and other domains, there has been a recent surge of interest in understanding it. So if you look at the literature, there are two types of performance analysis. One is to basically understand why SSL can help classification so much. Basically, it's using downstream tasks performance as a metric to analyze the performance and the reason why it works so well. Another perspective is from a generative model identification viewpoint, which is something, which is the angle that we're going to take. We take this perspective because it's downstream task independent. And if you understand this generative model identification problem well, you can use it to help a lot of other tasks like domain translation, which I will talk about later today. Okay, so what is our model? So we consider this nonlinear mixture model. We modeled the samples of the Qth view, which is xq is a latent vector going through an unknown but invertible nonlinear function. And this latent vector can be split into two parts. The first part, S, is the shared latent components across different views. Remember, the views are representing the same thing, so they should be having something that is shared in the latent, right? And the C part is private. So if I want to give you some example, you can look at this two views of handwritten digits, right? So in these two views, the S part is shared, which is the identity of 0, right? And the C part is the style information, basically how you write the 0, right? And the noise that you see here. And this G part basically is responsible for generating this Z from a latent dimension to the pixels that you can visualize, right? So that's our generative model. And similarly here, right? S part here is the dog identity, right? This model, we like this model because it's quite general, because we don't have specific structural assumption on G, except for that it's invertible. We want it invertible because we want to go back to identify S, because remember, still we want to extract common information from different views, right? So if it's not invertible, then it's very hard for us to identify S, at least just theoretically. So this is our task. We want to extract S. And how hard is this problem, right? Let's forget about the multi-view setting. I'm just looking at this nonlinear mixture model. Because I don't know G, right? I only observe X. So is even identifying Z from this model possible? If we take a step back to assume that G is linear, then you have this X equals to AZ, right? So this is exactly the branch source separation model that we have been dealing with for decades in the signal processing society. And it is well known that if you just look at this model, the model is not identifiable, even if you have a simple linear model, because for whatever solution A and Z that you found that can satisfy this model, you can just insert non-singular matrix Q inverse here and give you another pair of solutions that can recover your model perfectly, right? Of course, we have a lot of remedies. You can assume you have some structures on the latents. For example, if you know they are statistically independent, then you can use ICA to recover Z. If you know that A and Z are non-negative, then you can use non-negative matrix factorization, right? There are a lot of others. But the basic idea is that you assume structures and exploit those structures. But if G is nonlinear, then things become very, very messy. And in this 1999 paper, Hava Running showed that no, even you have a strong assumption on the latents, you cannot really go back and identify ZL. You can construct a counterexample very nicely to show that this is not possible. But because now this issue has stayed there for 15 years also, but when nonlinear representation, deep neural networks are getting popular, people tried to solve this problem again, and a lot of nice results that we saw from the literature. You can exploit more structures again, right? To help you identify the latents, for example, slow varying temporal correlation, or you can have some auxiliary variables observable, and you can have some prior information, so on and so forth. But these are mostly derived for single view cases, not multi-view, and also they are mostly use some sort of independence, statistical independence assumptions on the latents, which I would tell you, we don't really want that in a lot of cases for some reason. I'll show you. Our model, right, is like this. We have multiple views, and we have two parts in the latents, and we have two nonlinear functions that we need to deal with. In the literature, you can see some papers. For example, this one is dealing with a similar problem, but it does not have the private component, and it also assumes that this S has component-wise mutually statistically independent components, as I mentioned. We don't really want that. It's a stringent assumption. This paper deals with a similar model, but this G is shared across the views, which simplifies the problem. But this makes the model less general because, this is a generative model. If you have a very different views, right, like text and a video, using a shared generative model is not so reasonable. So it's less general. This paper also uses a shared G. So what's our solution, right? Our solution is like this. We construct two neural networks with we can FQ, F1 and F2 for each view, and we designate, right? We designate the first D dimensions of the output of FQ as the estimation for the shared component, and the rest as the estimation for the private component. Okay, assuming that we know that this D is the dimension of the shared components, and then we construct this objective function, this learning criterion, right? Because we know the shared part is really shared, so we are matching the extracted representations from the two views, and we also do this normalization and the whitening as we did in DCCA. Now this is very, very much like DCCA, except that we have this splitting of the output of the neural networks, and also we added the constraint that the FQ, this neural network, is invertible in the sense that this data can be reconstructed from the representation. Because when we map our data, we don't really want to lose information, right? Okay, what can we say about this criterion? Right, this is just a tweak of DCCA. Can we prove anything out of it? Now, before we present our theorem, here's the assumption that I made. Right, we assume that these three blocks of variables are independent, block independent in this sense, right? And we assume this basically means that the shared information or the content information and the style information are statistically independent. Which the rationale behind this assumption is that, for example, in self-supervised learning, right, you can combine very different styles with the same entity, right? So they can be combined arbitrarily. So assuming that they are independent makes sense to some extent. And this is a lighter assumption compared to ICA type assumption because we don't ask for element-wise independence, but just asking for block independence, right? And we don't want the element of S to be element-wise independent because, as you see in this in the handwritten digit example, we want to use this S to work as some sort of a cluster indicator, right? So if it's a cluster indicator, it should satisfy some properties like this. If I belong to this cluster, I should not belong to the other clusters, right? So this is clearly dependent, right? So we don't want to, long story short, we don't want to add too many assumptions on the latent representations. Okay, so here's our first theorem. Basically says, right, if the block independence condition is satisfied, and then, right, the compensation of my optimal solution and the generative model, the compensation is continuous. And when we have infinite data, right, assuming that we're working over a continuous space, then what we learned for the shared part output of our neural network of the shared part S hat is just a invertible transformation of the ground truth, which is nice because invertible transformation does not lose information, right? And also it disentangles the shared part from the the private part, right? The style, the basically redundant information is discarded, okay? And let me see if I have time. Yes, so let me show you the proof in one slide. It's actually very simple once you come through. So this is our optimal solution. This is a generative model, right? This is the compensation. And this part, now I use this to denote the output of my neural network, right? This should be the shared part. I'm matching this two function, right, over all possible, over a continuous domain of x1 and x2, which means I'm matching this two function, right, over the S and the C domain. Okay? Now, what do I really want to show? Because this is my output, right, of this part, and this is my output of the private part. I want to show that the two do not have do not affect each other, right? Which means if I look at the Jacobian of this vector, I want to show this part to be 0, right? And it's easy, actually. I want to show this to be 0, and I look at the partial derivative of this function, right, with respect to the private part, right? If this is 0, I'm good, meaning that the extracted shared part is not a function of the private part, which means I successfully discarded the private information. And because I've matched these two functions, right, then it means that I can replace H1 with H2. And H2 is a function of S and C2, and because S, C1, C2, they're independent. So this entire thing has nothing to do with the C1. So this has to be 0, right? Okay, at least that's, then we have, invertibility, right? So this, because we have invertibility, this is not a function of C1, it has to be a function of S, right? And there are a lot of details, but this is the gist of the proof, just in one slide. Okay, and we, of course, we assumed a lot of things like smoothness, right, differentiability, and the working over continuous regions. Otherwise, you cannot even take derivative. Anyway, but as a first theory, we'll come back to that point, right? At least from a high level, by making a lot of assumptions, right, we understood why the shared components could be learned from the nonlinear mixtures. So what about the private information? And private information, as I said, it could be representing the style information. And the style information is quite useful when you want to manipulate your generative model. For example, if you have a photograph that has a Monet style, you want to translate it to Van Gogh style, then knowing this information is quite useful to you, right? And we have a network, right? The output, the first part of the network is the shared. So the question here is, hey, is this part really representing the C information, right? The private information. Now, unfortunately, if you just use the previous formulation, it does not really output that. But remember, we have assumed that the shared information and the private information are statistically block independent with each other. Then if you add this constraint, and if you can enforce the constraint using your optimization procedure, then you can prove that, okay, not only the shared part is an invertible transformation of S, the private part that you learn is also an invertible transformation of the ground truth. Okay? That's the second part of the proof. And, okay, so that's, let me just summarize a little bit of what we have done, right? We proposed a multiview generative model that is more general than the models in the literature. We designed a latent matching network to extract shared information and the private information. And we proved that both of them are identifiable under our model with not so heavy assumptions. And this, because our model and our learning structure is similar to what we saw in DCCA and SSL, hopefully, right, our results can shed some light onto the effectiveness of this existing frameworks. But at this point, we were not very happy about our result. As you saw in the proof, I was using a lot of assumptions, like using infinite data, especially this. And this is when you look at this literature on nonlinear identification, this is really bothering because for the last 15 years or so, all the papers were using this assumption. Right? You don't really have a finite sample understanding of this procedure perhaps because this is not something like supervised learning. You have a clear metric for you to show why this, to have a textbook derivation for understanding finite sample performance. So let me just restate the problem, right? We were assuming that we can work on continuous space of our two views and enforcing this equality over a continuous space, right? Which is something that we can never do. What we can do is we do with samples, right? And we enforce this over samples. And so we were trying to, the next step is trying to understand if this works. It really works in practice if you run simulations, but to understand how the sample complexity or number of samples can plays a role in this procedure. Also, we were, in the previous proof, we were assuming actually the learner, the nonlinear mapping represented by my neural network is a universal neural network, can represent any function, but in practice, you always have approximation error, right? So we also want to take this realistic conditions into consideration. Now the proof is a little bit lengthy, but actually it's not the pipeline is simple. Here is the idea, right? Because what I want to show is this part to be 0, right? Overseeing and unseeing samples. I want this part to be 0, so that I can use this to serve as my success metric. Then, right, I first start with seeing samples by enforcing this inequality. Then I can characterize the violation over unseen samples. This can be done just by generalization analysis, right, for regression models. And then I have this. If I characterize this violation, then I can take this into consideration and using a numerical differentiation estimation for this Jacobian, and then I can estimate this how large is this residue, right, in expectation. And this shows some very reasonable trade-off, right? This is a Rademacher complexity of the neural network that I use, which is going to be increasing when I use a deeper and wider neural network. And this part is the approximation error, right, of my neural network. This part is going to be decreasing when I use a deeper and wider neural network. So it's a trade-off you have to take into consideration in practice. Anyway, so that's some things that we got for finite sample case. And about algorithm design, right? Let me quickly go through that. So this is not a very simple problem, not a trivial problem to solve, because you have neural networks in the constraints, and you have this block independence thing to enforce, and you also wanted this F to be invertible. A lot of things you have to take into consideration. So what we did was just to recast this by using slack variables so that we can get rid of neural networks in the constraints, and also we design a regularization term to enforce the block independence. So this I don't want to go into detail, but the idea of designing this regularization is based on elementary probability, right? Basically, it says that if two random variables are statistically independent, if and only if all the transformations of these two random variables are uncorrelated, right? So we're just using correlation over a lot of functions represented by neural networks, right, to approximate that. So it can be. So I can put everything into neural networks and through this to some, backpropagation solvers to help me solve the problem. Not solve the problem, right? Just tackling the problem, okay? Anyway, so some interesting results that we observed. So this is a pure simulation. We generated this circle as the shared components of my two views. Because it's a circle, so the two components are dependent, right? And then I add noise as the private components, Gaussing, Laplacian, whatsoever. And then right, I make the noise to the private part to be really strong. So the energy ratio S to C is like minus 6 dB, minus 18 dB. Because remember in the proof, right, it shows that no matter how strong the private part is, the shared part will still be extracted, right? So I want to test on that aspect as well. And then I use this structure. And this is the shared component, and this is the visualization of the two views, which is a mess, right? You cannot really see this circle from the data going through this nonlinear transformation. But then if you apply our method, you see that, okay, the extracted shared part has this structure, which really does have a one-to-one mapping, right, with the circle, which is exactly what we showed. And if you look at the C1, estimated C1 versus C1 is also having a one-to-one mapping. Similarly for the second view, which verifies our claims, right? And if you test then, if you check the mutual information of different components, you will see that using our regularization and our designed variable will also output numbers that are consistent with our theory. But this is just a simulation. Let me show you some more interesting figures using real data. So here I'm using two views of MNIST data, as I showed you, right? One view is clean MNIST, another view is rotated and noisy. And first, I want to evaluate the extracted shared components, and I don't really have ground truth for me to evaluate it. So I just feed this shared components to a very simple clustering method. Here I used k-means, and then basically it shows that no matter what you use our method, or you use DCCA, or you use Barlow Twins, they give similar results, right? So basically it means that they all learn meaningful, right? Indirectly mean that they learn meaningful representations of the digits. What is more interesting is that we want to see that if our independence constraint that we added could really extract the private information that represents the style, right? And because we don't have a ground truth, this is what we do. We have two views here, one view and a two view, right? We extract the content information from the second view, which means, for example, here the content information should be representing the number 3, right? And then we extract the style information from the first view, which should be representing the writing style. And because in our learning to enforce the mapping to be invertible, we, as a byproduct, we also learn a inverse mapping. So we use that inverse mapping as a generative model to see if we can generate new data that has the identity of the second view and the style of the first view, right? So this is what we did. So using our designed regularization for the independence, block independence, we can see that, okay, for example, here, you really extracted a 3, right? So this entire column corresponds to 3. And the writing style really corresponds to this. Writing style really corresponds to this, which is a success, right? Although the quality is not as good, but at least verifies our model, the effectiveness of our model and also our claims, right? And also, but if you don't use the regularization for enforcing the block independence of style and and the contents, you will see that, okay, no, this identity is not shared across the entire column, right? So it's a failure, which means this part in our proof, right? This part is really important for achieving this content and the style disentanglement. And we also had this. We also had this on some other real data. So this is another example. I have two views of this 3D cars, right? And the style, the shared information is the type of the car, and the C part encodes the angle, azimuth angle of the car, and this generative model encodes the elevation of the pictures. And we do the same thing and generate new data to verify if our designed criterion works, right? We extract the car type information from view 1 and also the azimuth information from view 2. Now this blue box means that you're using the independence regularization that we designed. And this nicely, right, integrates the car type and the angle from here. But if you don't use our designed regularization, then this does not really use the angle from here, right? Here it even mess up the car type. So again, right, verifies our claims. Okay, there are other real data sets in our paper if you are interested. So let me just conclude my talk. So what we did here is that we revisited some very important learning paradigms in machine learning, multi-view machine learning, DCCA and self-supervised learning, and we view them from a nonlinear mixture identification viewpoint, right? We imposed this model on multi-view data and trying to understand how to identify S and C, right? The two blocks of latents. And we provided some new insights from this viewpoint with analysis, and also we provided new functionality, right? Because if you look at DCCA and SSL, it does not really care about the style information, but we showed that with a regularization that is driven by latent block independence, you can really extract the style information, right, on top of the content information. This can help you to do domain translation, right, style translation. And we also, on the side, we also provided the finite sample analysis for this framework. And this is based on the paper from the last year and headed by my previous student, Dr. Qi Li, who is now with Google. Okay, that's all. Thank you.